Assalamu alaikum warahmatullahi wabarakatuh. Again, this is Dr. Ali El-Moursy in a new lecture for Digital Logic Design DLD. This is actually lecture number 18 for the adder subtractor circuits. There are many designs for the adder subtractors, and there are many circuits that we have to learn for adder subtractors. So in this lecture, we will cover more than one circuit. We will cover a set of circuits. And the material that we need in order to learn this lecture, before you go over this lecture, you have to go and review very well the concepts of the addition and subtraction in binary from chapter 1. So I'm assuming that we will not go and learn from the beginning how the addition and subtraction is being performed. Okay, in this lecture, we are generally, the general title for the lecture is adder subtract circuits, but we have more than one item to be learned here. So we will learn first the half adder circuit, then we have what's called the full adder circuit. They give it the nickname FA, half adder, they call it HA. Okay, we have also to learn what's called a multi-bit adder. We will take an example for this, a 4-bit adder. Okay, we will learn also the multi-bit subtractor. Okay, as an example, we take the 4-bit A subtractor, or in short, we can call it sub. And we will learn what's called the 4-bit adder slash subtractor circuit. Okay. We will shed some light also on some concepts for the what we call the how can I detect the sign and overflow, and sign detection. Okay, which we usually give this as kind of a training or something. Okay, to at homework. Okay, so now I want to build a circuit that perform the operation that we have learned in chapter 1. In chapter 1, we learn how to represent the numbers and also how to add and subtract numbers in binary. So first of all, we learn actually two methods or two representations for numbers. We learn how to add, subtract for unsigned numbers and for signed to complement numbers. If you still remember the 7 steps for addition and subtraction that we have learned from chapter 1, you can discover that the technique of addition and subtraction is kind of similar between the signed and unsigned. So we will first build a circuit that is generic in the sense that it can perform addition and subtraction for the numbers binary, whether they are signed or unsigned. So let's start by the assumptions of the numbers that we have. Assuming that I have two numbers in binary and I want to add them. My first assumption is to consider that the number A, I have number A and number B, and I want to add those two numbers. Just give myself a little bit of space here. I have number A should be added to number B. The first thing that I want to ask myself is what is the size of the numbers A and B to be added. We have learned in chapter 1 how to add different number of bits for numbers. What is the simplest case? The simplest case is to have an addition between two numbers a and b, and a and b, each of them is just 1 bit. This is the simplest case. So in this case, I will just assume that a is 1 bit, b is 1 bit, and I want to add a to b. If I want to add a and b, and each of them is 1 bit, we have learned from chapter 1 that actually I have the following options. I may add a 0 and b is 0, or a1, b is 0, or a0, b is 1, or a1, b is 1. In each of those 4 cases, what should be the output? Remember that I'm designing a circuit that I know its inputs. How many inputs for my circuit? The total number of inputs for my circuit are just 2 bits. 1 bit coming from A and 1 bit coming from B. The second question that I have to ask myself, and the numbers there definitely by definition are binary, 1s and 0s. The second question that I have to ask myself is, what is the size of the output for the circuit that I am about to build? So if I'm to draw a block diagram for my circuit, right now we at least define that the circuit has input A0, input B0, and the circuit should perform an addition between those 2 bits. How many inputs do you expect for this circuit? Okay? But this circuit is adding 1 bit to 1 bit. By the way, we call this circuit the half adder circuit, HA. We call this circuit half adder. How many outputs for the half adder? In this scenario, the result is simply 0. When I add A and B, A0, B0, and both are zeros, so the output will be, you can anticipate that the output will be just 1 bit. But what if I'm adding 1 to 0? That means I have, the result is 1. Also 1 bit here is enough. If I'm adding 0 to 1, again, 1 bit is enough. But when I add 1 to 1, what should be the answer? The answer should be, as we learned in chapter 1, here I have, since I'm adding in binary, I should have the result as a 0, and I have to send 1 to the carry out. So in this case, how many bits of results I have? I have 2 bits. Accordingly, so should I design the circuit for those special cases or for the most general case? I definitely have to design the circuit for the most general case. And I can deal with those special cases because actually I can consider that the output in all of the cases will be 2 bits, but this second bit only in this case equals to 1, but in all of those cases, the other output is equals to 0. So the output for a circuit that adds 1 bit from A and 1 bit from B is actually a circuit that will give me actually 2 bits. Okay? Those 2 bits, the value of 2 bits will depend on the values of A and B. But the circuit itself gave me 2 bits. So we agree that this circuit, we will call it what? We will call it the half adder circuit. And for not to lose the generality, I will design this circuit and I will give some names to the inputs and outputs. So I am building a block that will add 1 bit from A. Okay, I can call the inputs A, the input B, and the outputs will be S stands for the output of the sum, and C stands for the carry out from the circuit. So now I have analyzed the problem that I want to solve very well. I finished the first step in my problem. The first step in my problem is to identify the inputs and the outputs, and verify that they are all binary. So I want to build a block that has two inputs or two bits, okay, of input, two bits of output, and it's called half adder, and it is supposed to do what? To add the bit of A to the bit of B. Okay, so I am done with the first step in my design. The second step in the design, as we have shown in our last lecture, is basically to start with a TT. Great. The second step is to build a TT for the design. Okay. The TT for the design, since I already defined the inputs and the outputs, the TT is very simple. Okay. TT contains actually inputs, outputs, and I have two columns for the inputs, two columns for the outputs. Okay, we agree that we will call the inputs A and B, we will call the outputs S and C. Usually they call it C out. C out. C out. Okay, so can I fill in the TT? Yes, this TT is very simple because all what I have to do, that I know two inputs, 2 to the power 2 is 4. I have 4 combinations for the input, 0, 1, 0, 1, 0, 0, 1, 1. Okay, so I have filled in the input part of my TT. So I'm following the standard way of design. We have how many steps? Input definitions, TT, K-maps, equations, in the circuit diagram. We have 5 components or 5 steps to perform. We get the block diagram, we have our circuit here. Okay, now can I fill in the TT? Yes. What's this circuit is doing? It should add A to B and give me the output. So 0 plus 0 is 0 in the output and 0 in the carry out. If I'm adding 1 to 0, I have out. This 1 will carry out is 0. If I'm adding 0 to 1, also the output here is 1 and the carry out is 0. If I'm adding 1 to 1, the output will be 0 and the carry will be 1. So I fully define the truth table for the half adder circuit. Then comes step number 2 or 3. It's supposed to be K-map. However, do we really need a K-map for a 2-variable thing? The answer is no, because the K-map will be very. If you're still interested to draw it, there is no problem. Let's draw it. How many K-maps we need? We need K-map for S and K-map for C out. For S, I can draw the following K-map. K-map 2 variables. Here I have A bar A. I have here B bar B. And S is simply 0, 1, 1, 0. Have you seen this TT before? This came up before and this TT before? This is a very well-known logic gate. We have discussed it in lecture number 16. This gate is called, this gate is simply called what? So K-map here. This gate is simply, so the fourth component is supposed to be the equations. You know the equation for S? I'll give you enough time to think about it. This is simply an XOR, right, correct answer. So it is an XOR between A and B. That's it, okay? Only one gate. Definitely I can represent it as sum of mean terms or the max terms. This will be a bigger circuit. That's why we learned the XOR in lecture number 16, correct? Make sense? Okay, good. Now, next, what about C? Do we really need a KMAP for C? I don't think so. You know why? Because actually, C out has only one mean term. Okay, so there is no need for K-map. Even if I draw a K-map, I will find 0, 0, 0, 1. Here is A bar A, B bar B. I have only one mean term here. So actually, simply C out is simply AB. Okay, then step number 5, the circuit diagram. Can we draw the circuit diagram for this? We got the equations. The circuit is very simple. It is simply an XOR gate between A and B and an AND gate also between A and B. This will give me S and this will give me C out. Done. So the first circuit we learned today is called the half adder, and it is really a very simple circuit. Okay, we got its block diagram, its truth table, K-maps if needed, equations, and then the circuit. Okay, after we build the circuit, I can use this half adder whenever possible, whenever needed. If anyone wants to add 2 bits together and get the answer, I have the solution for them. I know the block that you need. You need the half adder. So I can put the half adder circuit for him. Agree? Make sense? Sounds good? Okay. So now, so this is actually the first thing that we have wanted to study. Let's jump from the first requirement to the third, multi-bit adder. Let us make our problem more challenging. Okay. What if I actually have A and B, each of them is 2 bits? Can I still solve the problem using the standard way? The answer is yes. Simply, here A and B will not be just 2 bits. I will have A0, A1, B0, B1. Can I solve this problem in a standard way? Let's see. How many inputs in this case? I have 4 inputs. 2 bits from A, A0, A1, 2 bits from B, B0 and B1. What about the outputs? If I am adding 2 bits together, okay, from chapter number 1, that's why Dr. Ali urged us to review chapter number 1. If I am adding those 2 bits together, what should the output look like? Okay, for the example here, I'm adding those. We learned the addition in chapter 1. So adding 1 to 0 is 1, and there is no carry out. 0 to 1 to 1, that means 0, and I have a carry out of 1. Okay, so that means when I'm adding 2 bits to 2 bits, the maximum I can get is exactly correct answer, 3 bits. Correct? And what if I'm adding, let's make this even more complicated. Let's make it hard, more hard, or tougher. What if I have A and B? Each of them is actually 4 bits. I have 2 questions. First of all, how many outputs do you need for this circuit? Okay. Following the add operation that we have learned in chapter number 1. Okay, we usually put those boundaries, and we will add the bits A and B. So we will get here what's called S0. Okay, and we get a carry from this bit, and then we have S1 carry, S2 carry, S3, and final carry here, which is called C4. So if I'm adding two numbers, A and B, and each of them is 4 bits, so I expect to see the output to be how many bits? 4 bits for the result and 1 bit for the extra carry. So I have a total of 5 bits as my output. So we need to design this circuit. So our second circuit to design today is actually a 4-bit adder. A 4-bit adder. Let's remove the block diagram for the, or can we leave it? It's okay. We can leave it. Okay. Now the challenge. Can I follow the same standard steps of design in order to design this circuit? First of all, can we see a block diagram for this circuit? So let's remove our half adder here. Okay. And also, let us remove all of the circuit for the half adder. We've already done the implementation of the half adder. But we have ended up, after doing all of this, by a block diagram for the half adder. You won't forget it. You want to recall it. It's a block that has 2 inputs and 2 outputs, called the half adder. It's adding A to B and gives C, S and C out as output. This is the block that we already have been built like before. But right now I need to build another block. This block looks bigger and more complex. Okay, the block to be designed here has the following inputs. How many inputs for that block? This block has 4 inputs from A, 4 inputs from B. Correct? These are actually has A0, A1, A2, A3, B0, B1, B2, B3. So 4 inputs from A, 4 inputs from B, as it's shown. And the outputs for this block are those 1, 2, 3, 4, and 5. Those can be named as S0, S1, S2, S3, and C4. Okay? What is this block? It's called a 4-bit adder. The tough question here. Can we follow our standard steps that we have followed to build half adder in order to build this block? The answer, unfortunately, is simply no. Why is that? Because this circuit has how many inputs? It has 8 inputs. How many outputs? It has 5 outputs. It is impossible for us to build the truth table for this, because you imagine how big is the truth table. The truth table will have 2 to the power number of inputs. So you have here 8 inputs. It's 2 to the power 8. That means 2 to the power 8 is 256 different rows for the TT. It's impossible design. No way. Not only that, if I succeeded to build the TT for this, okay, What will be my next step? K-map. Can you build a K-map for 8 inputs? We don't know how to do it. This needs some computer systems in order to build the K-map. Okay, so we cannot do it on the board, or we can't do it manually. So it is impossible. However, we may think about redesign for the problem. The engineers start thinking, how can I build this block without going into these tough difficulties? So they go back to the technique of addition that we have followed here in order to add those two numbers while we learn them in chapter number 1. In chapter number 1, what we actually did, do we add those numbers together as a whole at once and get the answer? The answer is definitely no. Actually, we followed kind of a baby steps, hierarchical way of design. Okay? Actually, if you review the technique of addition that we have performed in chapter 1, you will find the following. You will find that we have actually add the first two bits together, and we can produce what? Produce the, from adding A0 to B0, we produce S0 and C1. Can we build this circuit? The answer is yes. This circuit is called what? It's called half adder. Already built it. Right. Let's go to the next step. In chapter number 1, what the next step that we want to do? We need to add the inputs C1 to A1 to B1 and produce what? Produce S1 and C2. The question here, can I use half adder to perform this operation? The answer is definitely no, because actually half adder by definition adds two bits together and gives me S and C out. While the circuit that I need here is actually should add 1, 2, 3 inputs and give me S and C out as an output. Okay, so that's why we cannot use this block. We have to build another block. This block is called what? It's called the full adder circuit. This block is supposed to do what? To add A to B to C and give me S and C out as the two outputs. This circuit, if I succeeded to build this circuit, which we call it full adder, that actually adding A, B, C together, I can use this circuit to perform this operation. So I will get the S and the C out for the second set of bits. Then what? What about the third step? I need to repeat this circuit one more time, okay? To actually add C2 to A2 to B2 and produce for me LS2 and C3. Okay, so this block can be repeated to form the third operation. Then what? Again, I need this block to be repeated 1/3 time here to add C3 to A3 to B3 and give me S3 and C4 as the out. Okay, so what we did right now, we engineered the problem. Okay, can we draw the full circuit? We can build this circuit hierarchically. Hierarchically means instead of design it from the beginning as a standard problem, I dissected, I diluted, I partitioned it, I decomposed the problem into smaller blocks connected together to give me what I am looking for. Okay, can we see this design? Yes. So right now, I actually need, okay, the first block here is half adder. This first block is supposed to add A0 to B0 and give me the result as S0 and C1. Can you see this? And then what? Okay, I need in order to perform the second operation here, I need another block called what? Called full adder. This full adder is supposed to actually add the C1 coming from the output of the first block to A1 and B1, and it should give me S1 and C2 to perform the second operation. Then again, I need this to be repeated again, okay? Taking the output from the second block and add A2 to B2, okay? To produce what? To produce S2 and C3 to perform this third operation. One more time, I need a third block of half adder that actually takes the input from the previous stage and take A3 with a B3, add it to the C3 to give me the outputs S3 and C4. What we have done here is actually we engineered the problem, okay? So right now, what I have achieved here is this block. It's a 4-bit adder that has for its inputs 8 bits, 4 bits from A and 4 bits from B. Okay, those 8 bits, let us just put them with the same colors here to make them distinguishable. So I have A0, B0, added to, and this is A1, A2, B2, A3, B3. Okay, and this will actually produce for me the following signals. S0, S1, S2, S3, and C4. So this is identical to this. All what I have to do, I'll just flip the block for the half adder, flip the block of the full adder. Okay. So in order to realize this design, what is left for me to do is to build this full adder. We didn't build the full adder yet, but if we succeeded to build the full adder, that means we will be succeeding to build what we call the 4-bit adder. The 4-bit adder, which is the same. So the 4-bit adder is one half adder, 3 full adders connected back to back. Through these connections, I can achieve what I want. Okay. So right now, will we be able to build a full adder? The answer is yes. So let's take the design for the full adder in a offline here. Full adder design. Can I build the full adder block using the standard wave design? The answer is yes. Why? Because the full adder is a circuit that is supposed to add 3 bits together and produce for me 2 bits as the output. And this is manageable through the K-map, through the truth table. Okay? So here I can follow the standard wave design. First step, Block diagram, we already did it. Step number 2, TT. Can we build the TT for this? The answer is definitely yes. This is a very simple TT, okay? So the TT for the full adder is actually supposed to have here, okay, I can build it generally, okay, with a generic name. So I will call the inputs for any of those A, B, and C as the inputs for the full adder. And the outputs are S and C out. So the full adder circuit is a circuit that has 3 inputs and 2 outputs. Can we build it? Yes. Can we fill the table? 0, 1, 0, 1, 0, 1, 0, 1, 0, 0, 1, 1, 0, 0, 1, 1, 0, 0, 0, 0, 1, 1, 1, 1. Now, how this circuit is supposed to work? This circuit is supposed to add the 3 bits of the inputs A, B, C and give me the outputs S and C out. We already learned how to do that in chapter 1. Okay, so can we do it here? Yes. Adding 0 to 0 to 0 is 0 and 0 for the outputs. Adding 1, 0 to 0 to 0 is 1 at the output and 0 at the carry out. 0 to 1 to 1, 1 and 0 in the carry out. 1 plus 1 plus 0 is 0 and 1 in the carry out. 0 plus 0 plus 1 is 1 and 0 in the carry out. 1 plus 0 plus 1 is 0 and 1 in the carry out. 0 plus 1 plus 1 is 0 and 1 in the carry out. When I add 1 to 1 to 1, the output is 1 and the carry out also is 1. So through this table, I have actually defined the different combinations of inputs for the full adder. Okay, so what comes next? Step number 3 is K-map. How many K-maps should I do here? I should have 2 K-map. K-map for output S and K-map for output C out. However, if you look carefully on the S here, you will find S is 0, 1, 1, 0, 1, 0, 0, 1. And S match exactly the truth table for the 3 variable XOR. So S equals to A, XOR B, and XOR C. Okay, there is no need for K-map. If you don't believe me, let's go and build the K-map for S. If you build the K-map for S, you will find out that this is A bar A, B bar B, C, C bar, C bar. So it is 0, 1, 1, 0. 0, 1, 1, 0. 1, 0, 0, 1. 1, 0, 0, 1. If you closely reviewed this K-map, you will find it's exactly a K-map for an XOR. Okay? Fine. The second function that we need to build the K-map for is simply the C out. Okay? So another K-map for C out. So I need to build the K-map for C out. It has inputs A bar A, B bar B, C, C bar, C bar. And this is for C out. Can I fill it? Yes. 0, 0, 0, 1, 0, 0, 0, 1. Pay attention to the order. and 0, 1, 1, 1, 0, 1, 1, 1. Okay? Then the regular K-map simplification. Okay? Hold a second, please. Now I need to discover the prime implicants. So I have here this prime implicant for this contour. This contour is A, C. So I have the first A, C. Then I have the opposite one for those two cells. This is A, B. I have A, B. Finally, I have this contour. This is for BC. So I have BC. Second step is the essentiality. Is the first one essential? Yes, it has one cell not exist anywhere. But this is essential. Second one essential? Yes, it is essential. Third one essential? Yes, it is essential. Three of them is essential. That means the equation for C out equals to AC or AD or CB. This is the final equation for the output for the C out. We have the equation for S, so that means we are ready to go to the, we got the equations, which are step number 4 are the equations. Step number 5 is the circuit. Can we draw the circuit? Yes. I have here an XOR between three inputs, which we call them A, B, and C. This will give me directly mean the S for the full adder. Okay? And we have 3 AND gates. The first 1 AND gate, 2 AND gate, 3 AND gate. The first AND gate is between A and B. The second AND gate is between B and C. And the last one is between A and C. So these 3 outputs should be ORed together to give me the output C out. The circuit that we have just drawn here is actually representing the circuit diagram for the full adder circuit. Okay? So this is the truth table, K-maps, equations, circuit. More important than all of this is the block diagram that you can use it in order to implement other circuits. So right now we succeeded to learn the half adder circuit, the full adder circuit, and the 4-bit adder circuit. Inshallah, we will take a break, and after the break, we will learn how can we learn a 4-bit subtractor and adder subtractor circuits, and we will discuss the overflow and the sign, which we have covered in the chapter 1 for the signed and for the unsigned numbers out of this circuit. So this circuit is actually what you can design for a 4-bit adder. Before we close this issue and before we go to our break, I just want to ask a question here. What if I have A and B not 4 bits? If they are 8 bits or 16 bits, what kind of modification that you will do for this circuit? Simply all what you have to do is to just replicate more full adders here. Okay, so I can have full adder, okay, repeated as many times as I want with the connections. I can expand the circuit, and this is the other very high advantage of this hierarchical way of design. It is expandable, very easily expandable. Okay, so let's go into a break, and then we will continue in the other circuits and maybe discuss more about this circuit later on. Thank you.